You guys ever watch Wile E. Coyote cartoons? Right? He's up at the top of a cliff. And down here is the Roadrunner, right? So Wile E. Coyote is up here and he has a big rock. And he wants to push it off and have it land on the Roadrunner as the Roadrunner goes zipping by down the road. So, way up here at the top of this cliff, it's not moving, this boulder. But as soon as he pushes it over the edge, it's going to start moving. And it's going to have a lot of kinetic energy by the time it lands down here. And he's hoping, because he has food down here at the bottom, that's what he always does. He puts grain, hoping that the Roadrunner stops and eats the food. And of course, you know how it turns out. The Roadrunner eats the food and goes beep beep and takes off just as the rock hits the road without the Roadrunner there. So we call this up here at the top potential energy. So, okay, Noah's feet are sticking way out here, and this book is up pretty high, has a lot of mass. If I were to let go, could it hurt his foot? Sure, okay, because it has potential. It's not moving though, there's no kinetic energy, but because of its height above his feet, and then gravity acting on it, it's going to pull it down, and it's going to hurt his foot perhaps. So I dropped it real close. But the higher I could drop it, that mass is going to result in a significant amount of energy. So the formula is mass times acceleration due to gravity times the height that something could fall. Okay? If I held the book, instead of over his feet, I held it right here, the potential energy changes dramatically because now it can only fall this far. So the height is only this. I just pull it out here, now it's from here to the floor. So it's more potential energy. So the height is related to the height above the place where it could stop. All right? Kinetic energy is mass times the velocity squared, which is a pretty big number, and then it's 1/2 that. We're not going to talk about how you derive that formula. We'll just use it. Okay, easy formula to use. So this has a lot of potential energy here, so it's falling. Just before it hits the ground and stops, it has maximum kinetic energy. What is causing it to go faster and faster? Because when he first rolls it off, it's not moving. Gravity, right? So, what's interesting is, this is what we're going to talk about in this next section of the chapter, the potential energy here at the top has to be conserved. So all the potential energy here has to be equal to all the kinetic energy just before it hits the ground. So if we calculate this number, which should be easy to do, we could set it equal to this. We know the mass, so then you could easily solve for what would the velocity be. Because it will, the total energy has to be conserved. It can't be created or destroyed. All right, open your book to, whoops, too far. Make sure you read the box on page 243 about Mr. Joule. That could be a good test question. All right, so top of page 259, Law of thermodynamics says energy can't be created or destroyed, so the total energy, TE, has to equal PE plus KE, potential energy plus kinetic energy.
This looks like physical education.
Oh, yeah, physical.
All right, now, let's talk about a swing set. So, you remember riding on the swing, right?
Mm-hmm.
If you were just hanging here, not moving, okay, you don't really have any potential energy, no kinetic energy. You're not moving, no potential energy. But when you were a little kid, Dad would come behind you, right? Pull the swing up in the air. So let's say the swing ends up out here. Well, now this distance times the mass times acceleration due to gravity helps us figure out what is the potential energy. He's holding it though, so it's not moving. But now we have potential energy. As soon as you let go, the swing swings down, goes through this point, comes back out here, swings back, goes here, right? In a perfect situation where there's no friction
Or air resistance.
or air resistance, the potential energy, all the energy is potential energy. Here, there's no potential energy. It's at the bottom point. So it's 100% kinetic energy. So when we take the formula, total energy equals PE plus KE. Right here, KE is 0, so it's just PE. You get down here, and we only have kinetic energy and no potential energy. And then the energy converts back to potential energy here. You literally come to a stop for a split second when you reach that highest point. It turns around, starts swinging back. Okay, so the pendulum just keeps going back and forth. So the potential energy, kinetic energy at any point, we're at the maximum points here at 3 equal. But what's also interesting is, at some point in between, let's say the swing is right here, we still have some potential energy and we have some kinetic energy. So that's where this formula comes in. If you can figure out, well, how far above the ground are we, then you can figure out, if you know the total energy, subtract that, and you know the kinetic energy. If you know the kinetic energy and the mass, you can find the velocity. So that's one of the things we're going to be doing. In fact, if you look at page 261, there's a roller coaster. It's all written a roller coaster. No, okay. It's pulled to a hill, 113 meters high. It stops at the top for a second and then it begins to roll down the hill. It accelerates, okay, to the bottom of the hill, which is still 22 meters above the ground, and then it begins to climb another hill, which is 67 meters high. Ignoring friction, what is the car's speed when it reaches the bottom of the first hill and when it reaches the top of the next hill? Could we find the total energy of this system? Okay, where is its energy, 100% potential energy?
Up here at the top.
Yep, at the very tip top, the highest point. Okay, so if we take that height times the mass times gravity, we'll have the total energy, and it's not moving, so no kinetic. All right? But then when we move down, we have to figure out, well, how much potential energy does it have at that lower height? Subtract, we'll have the kinetic energy. All right, let's work our way up doing some simpler problems first. Come on up.
Good practice.